Good afternoon. Welcome to the Johns Hopkins Applied Physics Laboratory in Lowell, Maryland. My name is Dwayne Brown with NASA's Office of Communications. To set the stage for today's press conference, please welcome to the podium the Associate Administrator for NASA's Science Mission Directorate in Washington, D.C., Dr. John Grunsfeld.
Welcome, everyone. It's a full auditorium here at the Johns Hopkins University Applied Physics Lab. I was a little bit worried no one would show up. Actually, I wasn't worried at all. Anybody get any sleep last night? I'm not hearing too many affirmations of a good night's sleep. I'm not going to ask the team because I know they were probably pretty excited about this morning's data pass, as was I. I'd like to take you on a short tour to frame the discussion. I'm not going to say a whole lot. The first image that I'd like to bring up was taken just about 2 hours ago by the Solar Dynamics Observatory. I hope you recognize that object, and I think you know where we're going. Mercury, from the Messenger mission, Venus, from Magellan. If anybody doesn't recognize the next planet, I'd like you to leave the auditorium. APL security will escort you to Area 51. The red planet Mars, I had to get a Hubble image in there somewhere. I realize I missed Ceres, which the Dawn spacecraft is orbiting right now, Jupiter, with some of the Jovian moons in shadow. From the Galileo spacecraft, Cassini at Saturn. What a wonderful mission. This is just a striking image. Uranus, somebody made a wisecrack that I put it in sideways. Neptune, and for a grand finale, I turn it over to Alan Stern, the principal investigator of the Pluto New Horizons mission.
Well, before we turn it over to Alan, got a few words to say. Yesterday, America's space program took another historic leap for humankind. Today, the New Horizons team is bringing what was previously a blurred point of light into focus. We'll have presentations from our panel. We'll open it up for questions with media here, on social media, and we'll go to the phone lines. You can join the conversation on social media, Twitter, Facebook, at hashtag Pluto Flyby, and if you have questions on social media, send those in to hashtag AskNASA. And of course, the images and information you will hear today for more days and more weeks and months will be online at www.nasa.gov/New Horizons. You've heard from Dr. John Grunsfeld. Of course, Alan Stern needs no introduction. So I will go to Hal Weaver, who is project scientist from the Johns Hopkins Applied Physics Laboratory, followed by Will Grundy, New Horizons co-investigator, Lowell Observatory in Flagstaff, Arizona. He will be followed by Kathy Olkin, Deputy Project Scientist from the Southwest Research Institute, and John Spencer, another New Horizons co-investigator from the Southwest Research Institute. And with that, Alan, it's all yours.
Thank you, Dwayne. Well, I had a pretty good day yesterday. How about you? Well, New Horizons is now more than a million miles on the other side of Pluto. That's how fast we're moving, having made closest approach yesterday morning. The spacecraft's in good health. It communicated with the Earth again for a number of hours this morning, beginning about 5:50. We got data down from 5 of the scientific instruments already. We're going to report on some of those results, but frankly, we're just skimming the top of it. There's a lot in just the things we're going to talk to you about. We have big news from the first resolved image of Hydra, Pluto's outermost moon, to the discovery that Sharon has been active. Thank you. Go ahead. And there are mountains in the Kuiper Belt. You'll enjoy that. This system is amazing. Now, all of our news today relates to the surfaces of Pluto and its satellites. We'll be talking more about the surfaces in the press event on Friday down at NASA headquarters, but we'll also be bringing in atmospheric results at that point. I do want to report one piece of news, but it's more or less operational, and that is that the ALICE ultraviolet spectrometer got a great data set to the ground from the UV solar occultation, in which we're already learning things about Pluto's atmosphere, so stay tuned for Friday on that. So with that, I'm going to turn it over to Hal Weaver, who's our project scientist. Hal's going to give you a little bit of hydrotherapy. Hal?
Thank you very much, Alan. Well, Pluto and Sharon are going to steal the day today. I mean, this can be these awesome images that you'll see in a few minutes. But let's not forget that Pluto has 4 small moons as well that we want to collect data on. Starting from closest to Pluto and going out is Styx, Nix, Kerberos, and Hydra. And this morning we got the first really well-resolved images of Hydra, which is shown in front of you here at the native scale, 2 miles per pixel. This is about the same number of pixels across Hydra that we had across Pluto in mid-June. And so we're ecstatic about this. Prior to the New Horizons revealing of Hydra here, we were completely uncertain about how big Hydra was. It could have been anywhere from 20 miles across to almost 100 miles across. New Horizons has made it easy. Just count the number of pixels across. 28 by 19 miles, an elongated object. Hydra is not a planet. It's about 30% larger in one dimension than in the other. But there's some very interesting things about Hydra. You see some variations in the brightness across the surface. If you can go to the next slide. This shows, what we did here was actually subsample the image by a factor of 4 from the native, so it's 4 times subsampled to take away that pixelated look, and as well as overlay contours showing the brightness changes. And we took cuts across to measure that's the approximate places where you have the longest dimension in the green and the shorter dimension in the yellow. The surface of Hydra is surprisingly large. It's about 45% reflectivity. So about 45% of the sunlight incident on it gets reflected away, and that can only mean that Hydra surface is probably composed primarily of water ice. It's the only way to get it that bright. And that's cool. It's intermediate in brightness between Sharon and Pluto. A nice thing about what we have coming up, actually, some more observations of Hydra, which will be even higher resolution, about a factor of 2 or 3 better. And so we're looking forward to those, but it's great. We've already seen Hydra revealed, and it looks very interesting. Thank you.
Okay, very nice. Will Grundy leads our composition team and is going to report some results that they've obtained.
Okay, so the Ralph instrument is the instrument that we're relying on mostly for surface compositions, and it's composed of 2 parts, the color camera, MVIC, and infrared imaging spectrometer called LISA. We don't get any data down today from either of those instruments, and so what I'm showing you is some data that came down in the failsafe data set that came down overnight between the 12th and the 13th. So this is a little earlier. This is a base map that's just showing you the geometry. You can see that the heart region is just rotating on, so this was a little while ago. Could I have the next time step? This is an overlay of LISA data. So what I did is each of those large blocky pixels, about 150 kilometers across, is an infrared spectrum. And the value of an infrared spectrum is that it tells you what that pixel is made out of. We're going to get much higher resolution data than this, but this is what's in the can now in the fail-safe data set. These colors are just 3 infrared wavelengths. We get 256 infrared wavelengths, so we could make an enormous variety of color maps to pull out specific compositional information. This particular one is focusing on methane. I put a absorption band that's at about 1.65 microns into the blue color channel, a continuum region between 2 methane bands into the green channel, and a much stronger methane band into the red channel. And all I'm doing here is showing, again, at lower resolution than the color images yesterday, the diversity of terrains. What I'm going to do now is pick out a couple of specific regions, although you can see that there's many different regions here. So if I could get the next time step, please. These 2 regions of interest, one's a 3x3 pixel block, another one is a little squiggly thing that's in one of the dark regions. So I'm concentrating on the polar cap, and I'm concentrating on one of the dark regions. And if we go to the last time step that I have, these are the 2 spectra that you pull out. And you can see that they're quite different from each other. They both have methane, but the overall shape of the spectrum is very different, and we can really be spending years modeling these and thinking about what they tell us. There's a lot of information. We only have a small subset of the wavelengths at this point because we just don't have the bandwidth to get more down. But this is providing a lot of information about the different regions and how they work.
Thank you, Will. Yesterday, we showed you a beautiful image of Pluto that was made just before the closest approach and sent to the ground as a part of those fail-safe data sets. Today, we're going to show an image of a similar resolution on the big satellite Sharon, and Deputy Project Scientist Kathy Olkin is going to discuss those results.
So originally, I thought Sharon might be an ancient terrain covered in craters. Many people on the team thought that might have been the case. And so Sharon just blew our socks off when we had the new image today. So if we can pull it up so you can take a look at it. I don't, yeah. So we were just been thrilled all morning. The team has just been abuzz. Look at this, look at that. Oh my God, that's amazing. So I'll walk you guys through some of the things we've seen in the image and tell you what we're thinking about. And I'm going to start in the north and kind of work my way down. So you've seen the darkish area that is at the North Pole. And informally, we've been referring to that as Mordor. So that's awesome. So Mordor is the darkest area near the pole. And you can see this is a natural color image. And so the red around it, the red coloring that we've seen, extends beyond just the deepest, darkest part of that polar region, Mordor. And we think that the dark coloring could perhaps be a thin veneer. You can see locations at the North Pole where a crater has perhaps dug into that region and excavated underneath it. So you can see those brighter regions that may be craters. And so that's part of the reason why I say that we think it could be a thin veneer. So let's see. And also you can see that that area is kind of a polygon shape. So there's, and then the red color is more diffuse around it. Moving down across a little bit lower, going from the northeast to the southwest, is a series of troughs and cliffs. And that's just striking to me. It's amazing to see this image. They extend about 600 miles across the planet, so this is a huge area, and it could be that it's due to internal processing, and we will be looking at that in more detail. Just below that region, the line that you see cutting across from the northeast to the southwest, more east-west than north-south, is a region where it's relatively smooth. There's less craters, so perhaps it's been geologically active or recently resurfacing that area. So that's very exciting to see as well. Two features that I want to go back up a little bit higher on the near the top at about the 2 o'clock position, you see a canyon. You can see a long linear feature, and you can actually at the very top see kind of a notch where you're looking through to the space on the other side. And that canyon is really quite deep. It's about 4 to 6 miles deep. I find that fascinating. So it's a small world with deep canyons, troughs, cliffs, dark regions that are still slightly mysterious to us. There's another canyon on the other side at maybe the 10 or 11 o'clock position, and that one is about 3 miles deep. There is so much interesting science in this one image alone, and we have a higher resolution image that we'll get that won't cover the whole olive Sharon, but it'll cut across the northern part, and we'll get some of the dark area and then some of the middle area, and it's going to be about a factor of 5 better in resolution. As we've been saying, Pluto did not disappoint. I can add that Karen did not disappoint either. Thank you.
Well, yesterday when we showed that beautiful image of Pluto, we noted that we would have imagery with 10 times the resolution on the ground by today. And in fact, John Spencer is going to tell us about just the first frame of that mosaic that's already down on the ground, and which has already given us a big surprise. John?
Thank you, Alan. So yeah, we've got a whole bunch of high-resolution observations now safely on board the spacecraft, and this is just a taste, just one small part of one of those observations. And if I can have the first slide, don't get excited yet. This is what you see. This is what we saw yesterday, and this is a spectacular image. But we now are focusing in on small details on this amazing world. Before I go to that, I should say that we now have an informal name for the heart. The heart is a good name, but we want to honor the discoverer of Pluto, and this is now, we are calling this Tombaugh Regio. And so if I can have the slide back, we are now going to focus on a small region just near the bottom of this image, which is near the day-night line, where we have shading that throws the relief into sharp focus. And so we're going to be focusing on an area just a little bit to the left of the bottom of the frame. And if we can now run the movie. Okay, so we're zooming in on this area. Here's the image, here it comes. Yeah, that was our reaction too. So this is a small part of a mosaic that covers the whole of Tombaugh Regio and regions around it, covering quite a variety of terrains. But this is one of the first things that really caught our attention. This area, as you can see from the scale bar, is about 150 miles across. We're seeing features as small as half a mile here. You could see the APL campus on this kind of image. The most stunning thing about this, well, there's many stunning things, but the most striking geologically is we have not yet found a single impact crater on this image. This means this is a very young surface because Pluto is being bombarded by other objects in the Kuiper Belt, and it's bound craters happen. So we just eyeballing it, we think it has to be probably less than 100 million years old, which is a small fraction of the 4.5 billion year age of the solar system. It might be active right now. With no craters, you just can't put a lower limit on how active it might be. These mountains here that we're seeing were quite spectacular. These are up to 11,000 feet high. There may be higher ones elsewhere. Now, we know the surface of Pluto is covered in a lot of nitrogen ice, methane ice, carbon monoxide ice. You can't make mountains out of that stuff. It's just too soft. It doesn't have the strength to make mountains. So we are seeing here the bedrock or the bed ice of Pluto. We're seeing the icy crust. Water ice is strong enough at Pluto temperatures to hold up big mountains, and that's what we think we are seeing here. So the nitrogen and the methane are just a coating on top of this icy bedrock, and we're seeing that here. Now, what's particularly exciting to me about this is the first time we've seen an icy world that isn't orbiting a giant planet. All the other icy worlds we've visited have been moons of giant planets. And we see strange geological features on many of these moons, and we often or usually attribute this to tidal heating, deformation of these worlds by the gravity of that giant planet and interactions with other moons. That can't happen on Pluto. There is no giant body that can be deforming Pluto on an ongoing, regular basis to heat the interior. Charon is just too small to do that. So this is telling us that you do not need tidal heating to power ongoing recent geological activity on icy worlds. That's a really important discovery that we just made this morning. So I know this is just the first of the many amazing lessons we're going to get from Pluto, and there'll be more on Friday. We'll have more of this mosaic to show you on Friday, which is going to show equally amazing things, I'm sure, so stay tuned.
Right, and I'm going to follow up on this same image so we can leave it on the screen for you to enjoy. I'll tell you another couple of implications that we've reached as a result of this discovery. Just to expand on what John last said, which is very, very important, we now have an isolated small planet that's showing activity after 4.5 billion years. We thought this might be the case after Voyager 2 discovered that Triton, orbiting Neptune, also has virtually no impact craters. But we couldn't be sure for just the reason that John said, because there's always an out that tidal energy could have powered activity in tidal energy due to breaking into orbit around Neptune, could have been powering the activity on Triton. So that may have been the case for Triton, but it can't be the case for Pluto, and now we've settled the fact that these very small planets can be very active after a long time, and I think it's going to send a lot of geophysicists back to the drawing boards to try to understand how exactly you do that. There's another implication, and sometimes things work out in science. A couple of months ago in May, Kelsey Singer, who's a postdoc on this project, and myself submitted a paper to the Astrophysical Journal making some predictions. To follow up on that, as John said, the steep topography means that the bedrock that makes those mountains must be made of H2O, of water ice. So even before the composition team tells us that they found places where the nitrogen veneer has been eroded or scraped off, and we see water ice on Pluto for the first time, we can be very sure that the water is there in great abundance. And actually, models predicted that, but it's nice to see it driven home. Well, the other thing that means, as John said, is that the volatiles are just a frosting, just a veneer on the surface. Now, the sticky point in this is that Pluto's atmosphere is being lost to space at a rate of a few times 10 to the 27th molecules per second, tons per second, and over the age of the solar system, that corresponds to the loss of an equivalent layer of between 300 meters of nitrogen and 3 kilometers of nitrogen. So if we only see a veneer, which we now know, what's going on? What Kelsey and I predicted in that paper is that if we saw steep topography on Pluto, and therefore we're seeing only a volatile veneer, then there must be internal activity that's dredging nitrogen up through cryovolcanism or geysers or some other process that's active into the present on this planet. Now, we haven't found geysers and we haven't found cryovolcanoes, but this is very strong evidence that'll send us looking as we get more and more data across the surface of the close approach hemisphere to look for evidence of exactly these phenomena. Interestingly enough, that paper submitted in May was accepted today. How's that? And I should point out that the editor of the journal is only learning of the results we're telling you now because she's watching it. All right, well, that summarizes the primary things that we want to tell you about the data that landed just this morning. Each of these images and data sets have a lot more to tell us about Pluto's history and about small planets and how they are formed and evolve. I just want to make one more comment about Tombaugh Regio. You know, we could see the heart very far from Pluto. When we were still 70 million miles out and only barely resolving the planet, a little better than Hubble can do from 3 billion miles away, you can see that shining like a beacon. And because it's the brightest and most prominent feature on the planet, that's why we want to informally call it Tombaugh Regio, for the discoverer of Pluto. One more hand for the Tombaughs, please.
Ladies and gentlemen, before we take questions from the media here and on the phone lines or on social media, I want to take a moment to say it has been a remarkable week. It has been magical, and as we transition from the Johns Hopkins Applied Physics Laboratory here to NASA headquarters to do press conferences, the world has been watching. Dr. John Grunsfeld, 5-time Space Shuttle flown astronaut, Hubble repairman, and head of Science Mission Directorate of more than 100, almost 100 missions, with New Horizons being one of them. He is a household word, household name, and households nationally and internationally. Alan Stern, yes you are, exclamation point. And the New Horizons team and the Johns Hopkins Applied Physics Laboratory, household names. Show the world how much you appreciate that and what they have done this week with a nice and as loud as you can round of applause for their accomplishments. Okay, now let's get to the questions. If you can raise your hand high, we have a full house. I want to make sure I can get as many as I can and see you clearly. Let's start with here, and wait for the mic, and give your name and affiliation, please.
Thanks. Irene Klotz with Reuters. There's a lot to digest, but so I guess one of the first questions I had is for Kathy. Does the realization that Sharon is active have any implications for the origin theories, that it was a splat off of Pluto and another body? Thanks.
I don't think there. I don't know quite yet. So what I'd say off the top of my head is that I was thinking we would see lots of craters, and that would tell us something about how long ago Charon accreted, and so that would tell us something about that giant impact. The fact we don't see those craters makes that difficult to do, but I don't know that we are going to have to put our thinking caps on and understand how this all fits together and what it means. So this image just came down today, and we're making a lot of it right now, but that's my comment.
I could
yeah, yes.
just add briefly. We don't know how many craters are on this. This image has been compressed. Some details are obscured. We get better images, as Kathy said, tomorrow. And so speculating now would be especially embarrassing because we'll be proved wrong very quickly. But Sharon would have been tremendously heated in the impact, or the material that reaccreted to form Sharon would probably have been pretty warm. But this looks like it's something much more recent. So again, we have a story that we have some way of keeping heat going, keeping activity going in these objects for quite a long time.
Rick Lovett, freelance. Those mountains look really big. Do you have any theories of how they originated? I mean, are they volcanoes or tectonic? They don't look tectonic.
We have no idea at this point.
You might say something about their heights.
Yes. We mentioned that they're about 11,000 feet high, so, and they look to be tens of miles wide. So these are pretty substantial mountains. They'd stand up respectably against Rocky Mountains or other significant mountain ranges here on the Earth. But we want to see a lot more about the distribution, and we're just getting so much data soon that right now we're still scratching our heads.
Yeah, Kelly Beatty from Sky and Telescope. John, just to follow Irene's question, the large gash across Charon, is that in any way related to a tidal de-spinning, or is this plus the smooth areas telling you that there's something churning inside in a relatively recent time, and can you put a date on that yet?
Now, we've got to count those craters, and we've got to have better images to do that. We certainly know there aren't very many craters, but in terms of the timing of all this, we'll need the better images that we'll get very soon.
Sir?
Chip Reed with CBS News. Dr. Stern, I'd like to ask you a question with no scientific words in it. When I interviewed you before the flyby, and the only prediction you would make was that we would see something wonderful. Have your expectations been met? And what's the most wonderful thing you've seen so far?
Well, I'll give you a technical answer. You think? You think? I think the whole system is amazing, and my prediction written 20 years ago on a little slip of paper held in a manila envelope since 1993 was proven right by New Horizons. The Pluto system is something wonderful.
Bill, did you?
Yeah, question for Kathy. Bill Harwood, CBS. The structure of that dark northern region on this photo is so much more different areas seem to be within that area. Does this inform anything about the atmosphere, the Pluto atmosphere transport thoughts we've been talking about, how this material was deposited on the surface? Thanks.
Yeah, so there's definitely different subregions inside that region, and you can see it in this picture, and if you zoom in, you can see it in more detail as well. There are a number of different theories about what that dark region might be. I don't know that the distribution of the darker parts within it actually in detail inform that. To really inform that, I'm looking forward to getting the spectroscopic information back from the Ralph instrument.
And another aspect of that I'd add is I think a lot of us are looking forward to the stereo data, because then we can do the topographic reconstruction. If that's a basin, it'll be pretty obvious, for example. And if it's a raised plateau, that would mean something else.
Yeah, Nick Stockton, Wired Magazine. With regards to both the features on Pluto and Charon, what besides tidal energy could be powering active geology?
We think well, okay, let me think. We're still quite scratching, as you can tell. But I say we have a couple of options. One would be that we know there's radioactive material inside Pluto and Charon, as there is inside any body made out of average solar system stuff. And radioactive heat is powering a lot of the geology on the Earth. But the Earth is a lot bigger and can keep hold of that heat. So this may be telling us that even very small bodies, if they're icy, radioactive heat is enough to produce this activity. But there may be ways a body can store heat from its formation for a very long period of time. Maybe you can have an ocean which is very gradually freezing, and as it does gradually freeze, that releases heat into the crust, and maybe that can power activity. And so whether this is the heat generation is ongoing or it's still living off this reserve of stored energy from its formation, that's for a lot more work to decide.
But one thing that we can say for sure is that tidal energy is not at work here, and we know that because Pluto and Charon are in tidal equilibrium. Charon orbits in the equivalent of geosynchronous orbit, and it is also spinning at the same rate that Pluto spins, so there's no significant exchange of tidal energy anymore. That process, according to models, numerical models, took place pretty quickly after the giant impact, very small fraction of the age of the solar system. So that must have all been a long time ago, and it's not contributing to the energy budget currently. We have to get a little more clever.
Okay, we're going to take 3 questions, please. 1 question only so I can get to as many media. Then we're going to go to the phone line, take a couple of questions from social media, and come back here.
Cliff McMurray, Astro Magazine. I'm one of the people in the room that can remember when the first pictures came back from Mariner 4. And at that time, you could hear the balloons popping. Holy mackerel, it's not Earth-like at all. There's craters. The atmosphere is 10 times thinner than we thought it was. And today I see a lot of excitement and a lot of cool stuff, but I don't hear any balloons popping. It seems that Pluto is pretty much the kind of world that you thought it was going to be. Would you like to comment on that? And is that just because we're that much further along in our knowledge today?
Well, I will say that I'm completely surprised, and I would sort of disagree with the assertion. In my case, I certainly didn't expect Charon to show nearly the degree of different terrains, variety, or the youthful surface that it does show us. That's a complete surprise. That's a balloon popping. In addition, I think just having one image of about 1% of the surface of Pluto, the planet, and finding mountain ranges like the Rockies is a balloon popping. Now, my colleagues might disagree with me. Why don't we ask them?
Well, who would have supposed that there were ice mountains? You know, I mean, and you know that we can. You know, it's just blowing my mind. I mean, we have had such a hard time finding any evidence for water ice on the surface of Pluto. In fact, we haven't yet. We're going to have some data that's going to, really reveal that for sure. But that's the only way to get these huge mountains, and that's a big surprise, I think.
Yeah.
Go ahead.
I could speak to that as well. That false color image yesterday that showed an amazing diversity of compositional units on the surface, and the photographs that show an amazing diversity of morphology, geomorphology on the surface, points in my head to a great diversity of processes that are shaping the surface. And I think all of us thought it was probably a few processes that were at work, and now it looks like this is a much more complicated system where the interplay of physics and chemistry and thermodynamics is leading to just a huge palette of processes that are working in different ways on different parts of the surface. And that to me is amazing. This is going to keep us busy for a long time to come.
Oh, can I just...
Go ahead, John.
I would never have believed that the first close-up picture we get of Pluto didn't have a single impact crater on it. I mean, that's just astonishing.
Emily Lakdawala from the Planetary Society. I'm wondering if Will Grundy could read the spectra for us and tell us if you see any dips and squiggles. And while you're getting that on the screen, if it's time for us to consider that maybe the Sharon-forming impact could have happened more recently, and that might explain the recent-looking geology.
I think one more time step past this one is right. So these spectra are both methane ice spectra, really. All of those dips that you see are methane ice. The other features are much more subtle, and they're going to require some modeling to pull them out. But just to draw your eye to the right-hand side of it, you see how the cyan or blue-colored one goes down to almost zero, and the red one doesn't go down to zero. That tells me that there's something else present in the red terrain that scatters light where methane absorbs quite strongly. So there's an example of the sort of thing that you do. We could go, corner me later and we can chat as long as you like about this kind of stuff. I don't want to put people to sleep, but there's a huge amount of information in these data.
Okay, let's go to the phone line. I believe we have a question on the phone line. Do we have the question?
Can you hear me?
I can hear you now.
That's Keith Cowling, NASAWatch.com. The question I have, I actually had hoped to ask last night, but the NASA line didn't work, but I'm glad it didn't because I'm now looking at the IR spectral image that was just referenced. A question for Alan Stern. What specificity are you going to be able to get with this information from Ralph and Alice as you go on? And how will you be able to map it up against the terrain? You talked about a thin veneer of this stuff. I mean, some of this stuff is starting to look like waste I saw when I was teaching organic chemistry. Will you be able to map where this stuff is coming from and down to the point of more than just methane, but very specific organic chemicals?
I had a hard time. Yeah, I had a hard time. It was not loud enough.
Keith, could you speak a little louder and repeat? We apologize. Repeat the question one last time.
How much specificity will you have in the IR spectrometry against surface features such that you can see very specific organic chemicals mapped against these features?
Okay, I think the question is about how well we'll be able to determine the composition of the surface and spot other organics on the surface. We're going to have very high resolution compared to what Will is showing you here, about 100 times, well, not quite 100 times, but certainly spatially we're going to have down at roughly the 5 to 10 kilometer range. So in every pixel that Will is able to show you, we can look at things 10 times smaller, 1% smaller by area, which means that we don't average over large blocks of terrain, but instead can really see the details, the interfaces between units, look inside any craters that we find that are windows into the interior. Now I'll let Will speak to the range of organics that we could find on the surface because that's his area.
Right, so there are a lot of different chemicals that have diagnostic features in this wavelength range, and that's why we picked this wavelength range. But there are also substances that have no visible absorptions. A good example of that is argon, which is chemically a plausible constituent of that surface environment, and we just can't detect it because it doesn't have any vibrations in our wavelength region. The Alice instrument will be able to see it if it's in the atmosphere, but on the surface we're blind to it. And it's a mixed bag. We'll be able to learn a lot more than what we know about it today.
Can I add to that?
Maybe Will could give a couple of examples of light hydrocarbons that we could expect to find on the surface.
Sure. So the alkanes, for instance, which are things like carbon chain with hydrogen stuck to it, we could distinguish between methane, ethane, propane, and so on. Polycyclic aromatic hydrocarbons, some of them have very distinctive features. There's a wide range of organic compounds that we can hope to detect that could quite likely be produced in that surface chemistry.
I was just going to add that there's other ices also that have spectral features in this region. There's water ice, carbon monoxide ice, nitrogen ice, as Will said, this is a very diagnostic region. And not only that, you can see slopes across the spectrum. So even some things that don't have sharp features, you can identify the possibility that they're there by the slopes in the infrared spectra.
Okay, let's see what's going on in the social media world. I know it is a buzz, so we're going to turn it over to Emily.
Yes. I'm Emily Perfaro from NASA headquarters. We do have a lot of questions on social. The first one's from David, and he asks, what, if anything, can we learn about our own planet from this information New Horizons has provided?
Sure. Who wants to take a crack at that?
I'll let you go.
Okay. Well, we expect that the data sets that we'll return will teach us a lot about the formation of the Earth-Moon system. And we're really looking forward to doing that. We're also going to get atmospheric data sets that will let us study the escape of Pluto's atmosphere. In fact, the SWAP instrument combined with the ALICE instrument should give us very powerful constraints on that escape rate. Interestingly enough, Pluto's atmosphere is escaping through a process with a big fancy name called hydrodynamic escape that you just don't find on any of the planets in the solar system except Pluto. Now, the most interesting thing about that is that that same process did operate in the early atmospheres of a number of planets, including the Earth. In fact, the Earth is believed to have lost its original poisonous hydrogen-helium envelope due to hydrodynamic escape. So we've never been able to study this on a planetary scale, yet by going to Pluto and observing that process and determining exactly how fast the atmosphere is escaping and knowing the input conditions, the solar flux at the time that we made the flyby, for example, and the heliospheric radiation environment in the plasma, will give us a good handle for the first time on the numerical models that are used to understand the early Earth and the loss of our atmosphere. This also has some applications to the loss of water from early Mars. So we're really looking forward to learning things from the Pluto system that will ultimately translate into a better understanding of other planets in the solar system.
Okay, Emily, we're going to take two more questions. I'm going to ask the mic handlers to help me here. I know some folks have been raising their hand for a long time. I really want to get to you. So if the mic handlers, if you know someone has been raising it, give them the mics or cue them up and help me. But let's go back to social media. Two more questions, then we're going to come back here.
Sure. This one's from Harold. He's asking, how large of a percentage of Pluto will be viewed by New Horizons, and will there be any blind spots?
Mm-hmm. Kathy, you want to take
Sure, I'm happy to take that. So we're going to cover the entire illuminated part of Pluto, all the parts that rotate into view. It takes 6.4 days for Pluto to rotate. So we'll have some at higher resolution, some terrain at higher resolution than others. But there's, just like on Earth, when you have the winter pole and it's dark there, the sun doesn't rise. There's something similar on Pluto. So that winter pole of Pluto, we're going to make a special observation to try and observe that. And we're going to use the light that goes from the sun, it reflects off of Pluto's large moon Charon, and then reflects to Pluto. And we're going to use Charon shine to look at the winter pole of Pluto. So we'll be seeing all of it, but at different resolutions.
And just not to get your hopes up too much on the Charon shine, this is a very difficult observation. Yes. Charon shine is incredibly feeble, and we'll do the best to pull detail out of those images. We're also looking back towards the sun with the sun in our eyes, just to make it more difficult. So we're going to have fun pulling detail out of that, but we'll certainly do our best.
Yes, thank you.
One more?
Sure. This question's from Will. How do you think Pluto has been able to maintain its own geoactivity for so long?
Well, there's a great question.
Right. Certainly, if you have silicate rocks, and Pluto pretty much has to have silicate rocks in its interior to make its density come out right, because water ice isn't dense enough. Silicate rocks come with thorium and uranium and various radiogenic elements that give off heat as they decay. The naive expectation, or naive now in hindsight, was that a world this size just wouldn't get enough heat to really drive this kind of activity. And now we see that it can. Or, like John said, there's a lot of heat in an internal ocean, and as the internal ocean freezes, that liberates the latent heat. and also will tend to make the world expand in size because ice is larger than liquid, depending on which phase of ice you make, which could also produce tectonic features.
And I want to thank the world that on social media, sending your questions at hashtag AskNASA, and of course following the conversation throughout the world on hashtag Pluto Flyby. Okay, Mike Allen, so help me out. So name and affiliation, go.
Corey Powell with Discover Magazine. Back to that question about the diversity of processes that you're seeing in this new close-up Pluto image. I'm wondering if you could walk us through the image a little bit. I realize you're not at the stage yet where you can provide answers, but I'd just be curious about the kinds of questions that you see posed by this strange sort of hilly terrain and sort of hummocky. There's something that looks like a fault. I'd be curious, just sort of what are the things that you're going to be investigating there? What are the questions that it raises?
Those are good ones.
Yeah. You did a very nice job.
Well, yeah, we have this surface that looks kind of hummocky and something that looks like a fault, and yeah, that's kind of the stage we're at. And that terrain down towards the lower right looks really strange. And it's like piles of stuff with grooves on it, and to be technical. And then we have smooth plains filling in some of the low spots that we can say more about on Friday, I think. There's been erosion, there's been mountain building, there's been whatever produces lumpy terrain with grooves on it, and it's baffling. It's baffling in a very interesting and wonderful way. And I hope that when we get more context and we can fill in how this fits in with the rest of the geology, it'll start to make some sense. We can only hope.
I'm Alan Boyle with NBC News, and I wanted to return to the ice mountains as well. Is that actually in Tombaugh Regio? And do you see any pattern, following up on what Corey was asking about, do you see a pattern that might suggest the formation of those mountains? Are they being pushed up like ridges? Alan mentioned the Rockies. Is there a similar process going on here? Thank you.
Yeah, this is right at the base of the heart, if you like, sort of where it wraps around the edge of the whale, which is now Cthulhu Regio informally. But it's still in the bright terrain at the base of the heart. So that's where this is. Again, in terms of the distribution of the mountains, we'll just have to wait to see when we get the bigger picture view of more of the surface, and then things may make more sense.
Claire McMurray at Astra Magazine. Some of the features on that very good resolution square are kind of long and thin, and my eyesight's not the best. I can't tell whether they're trough-like or hump-like, and maybe you're waiting for the other direction image. Could they possibly be similar to lava tubes?
I don't see anything that leaps out to me as looking like a lava tube. Some of that surface looks maybe like the surface of a lava flow, but on a vastly larger scale. And so I don't think it would be the surface of a lava flow, but maybe some analogous process that's happening on a bigger scale. Yeah, that's... maybe I should comment that, yeah, there are a lot of sort of linear parallel features, as you say, and maybe it's folding of the surface, some strange kind of erosion, but yeah, we'll have fun figuring it out. And I should say, we will get, I'm not sure if this exact area is covered at high resolution, but it probably is. But I think we will have even more detailed images of this area, and certainly of other areas nearby, when all the data comes down.
Leo?
Leo Enright with Irish Television. Your findings on internal heating today, are they a game changer for the way that we should be thinking about other objects in the Edgeworth-Kuiper belt? I'm thinking in particular, if I could take it to the extreme, does it raise the prospects of water worlds out there, and does it increase the excitement about what we might see out there?
You want to take a crack at it?
Oh, I'll take a crack at it, sure. Yeah, I think it could be a game changer. We don't know. Charon is the size of some of the smaller worlds in the Kuiper belt, and Charon, we don't know how recent the activity is on Charon, and again, until we can start counting the craters, but It's clearly had things happening geologically fairly recently, and I think we've tended to think of these mid-sized worlds, Maki-Maki, those kind of objects, as probably candy-coated lumps of ice, and this means they could be equally diverse and be equally amazing if we ever get a spacecraft out there to see them close up.
Okay, we're coming up on the top of the hour. I'm going to try to get as many as I can, and we've got a cluster here, but we're going to have to shut this down in a moment. Go ahead.
Josh Sokol, New Scientist. I noticed today we haven't talked about any of the familiar touchstones, other worlds in the solar system, or moons we've explored that we could think of as analogous to Pluto and Charon. Is that because they don't look similar enough to make any insights, or how much are we going to be able to use what we already know from exploration to understand what's going on?
We're starting to make those analogs, and so the first thing is this doesn't look like Triton, which is the world that we have thought up to now is the most similar object in the solar system to Pluto. Triton doesn't have this kind of rugged terrain. It has a lot of strange materials, but it doesn't look at all like this. There's something very different about Plutonian geology. And Charon looks a little bit like some of the moons of Uranus, I would say. Ariel, Titania, where we have invoked maybe tidal heating as an explanation from tidal heating from Uranus itself. And as I said, now we're seeing that we can get this kind of activity on worlds that do not have tidal heating. Then we'll have to go back and look at those.
And I can add to that. Part of the reason you're not hearing us say Pluto looks like this world or that world is because Pluto has so much diversity. We're seeing so many different features. Like Will said, there's lots of different processes going on here. And so we'll probably end up pulling it apart and say this part resembles that on this world, but there's nothing like it.
Okay, so we're going to take two quick questions, and then unfortunately I'm going to have to end. If you have questions, we'll see if we can follow those up at a later time. Go ahead.
Thank you. Tarek Malik with space.com, and I think this question may be for Alan or whoever you want to delegate to. But you've shown us a first look at Hydra activity on Charon, ice mountains 11,000 feet tall on Pluto. And I'm just wondering today in the mission operations room how that feels to see it come down, to open it and know that yesterday you had one photo. Now you have something 10 times better, and tomorrow it's going to get even better. Thank you.
It feels terrible. Yeah. There's a lot of depression in the science team because we don't understand anything. People were thinking of just catching flights. No, honestly, it's I said a few days before closest approach that there were a lot of smiles because we could feel the momentum. We were finally getting to the stage where we could see geology and then topography on the surface. But now, I think I could characterize the 4 individual rooms where people are at work as something close to bedlam. Because, and particularly today's probably our biggest challenge. First, we're definitely living on less sleep than normal. But the imagery came down beginning just before 6 a.m., and this event began, 9 hours later. We have more data that's coming down today, but the next time we talk to you is in 48 hours, so we have many times as long to work with the data and discuss what we think the results are. And then the next time we come back and talk to you will be yet a week later still. So this is really, hot off the press. But I don't think, and I asked my colleagues to pitch in, I don't think any one of us could have imagined that it was this good of a toy store. Anybody?
This is what we came for.
This exceeds what we came for.
Okay, Frank, take us home.
It's Frank Mooring with Aviation Week. Last week,
I believe you were surprised by the difference in color between Charon and Pluto. Have you seen anything since yesterday that is beginning to inform that question?
I can speak for myself. I don't think so yet. But one of the interesting things that I think I'll just remark on is the image that we showed yesterday showing very strong color contrasts on Pluto's surface. I wouldn't be surprised if there are some units that might be Charon-like. We'll have to see when we get the higher resolution and more global color data sets. So we'll take a look. But something is making these two worlds very, very different. One has an atmosphere and volatiles on its surface. The other does not. One is covered in water ice. The other is covered in these volatiles. It's a puzzle. It's a real puzzle.
Okay, we're going to end here. As you've heard, this is just the beginning. The story is far, far from being over. We will transition to the next news conference at NASA headquarters at 1 p.m. Eastern on Friday. There will be more information and advisory going out tomorrow. Follow the mission and the incredible images and information on social media. Join the conversation, follow the conversation, hashtag Pluto Flyby, and send those questions in at hashtag Ask NASA. And of course, all of this information is online at nasa.gov/New Horizons. It's been a remarkable week. The NASA, New Horizons, and Applied Physics Lab, and all of the partners on this mission are truly household names throughout the world. Thank you for joining us here at the Applied Physics Lab. We'll see you at NASA headquarters.